Section 4.1, Exponential Functions. In this section, we'll evaluate exponential functions. We'll find exponential functions that model growth or decay. We'll use the compound interest formula, and we'll evaluate exponential functions with base e. Exponential growth is an increase based on a constant multiplicative rate of change over equal amounts of time. So, for example, the population of a city increases 2% per year. So, for example, if the population, say, started with 10,000 people in year 1, to find how many would be in year 2, I would take 10,000 and then add to it 10,000 times 2%. To find out how many people would be in year 2, and in year 3 we would continue the process. So a constant multiplicative rate of change. Here's another example. A salary increases by 5% per year. To find the salary in the next year, you would multiply the previous salary by 0.05 to find the increase. If a quantity decreases by a constant multiplicative rate of change over equal amounts of time, we call it exponential decay. So growth, if the amount is getting larger; decay, if the amount is getting smaller. Let's take a look at the difference between linear growth and exponential growth. In linear growth, the original value increases by the same amount over equal increments in the domain. So, for example, rent increases by $150 per year. If your rent starts out at $1,000, to find the next year's rent, you would add $150. So this time you're adding, not multiplying. So when you're adding the same amount, this is linear growth. If you're multiplying, then it's exponential growth. So in exponential growth, the original amount increases by the same percentage over equal increments of the domain. So for example, your rent increases by 2% per year. So if your rent starts at $1,000, the next year would be 1,000 plus, and now we're going to increase it by 2%. So we're multiplying rather than adding. The general form of an exponential function, if we were to look at the general form for writing an exponential function, exponential functions have this form that looks like this. F of x is equal to a b to the x. So b stands for some base. If the base is greater than 1, the function models exponential growth. And if b is between 0 and 1, the function models exponential decay. And we'll take a look at a few examples. So f of x is equal to 2 to the x. Here we have a base of 2, which is greater than 1. So this is a model of exponential growth. If you were to think about some of the values for this function, if x is 0, the function value would be equal to 1. If x is 1, 2 to the first is 1. 2 to the first is 2. If x is 2, 2 squared is 4. If x is 3, 2 cubed is 8. And if you were to think about how this is growing, all right, so it's going to go through the point 0, 1, 1, 2, and then you can see that it grows faster and faster and faster. So that's a picture of exponential growth. For exponential decay, here we have a base of 1/2, a base of 0.5, and this would be an example of decay. If we were to make a table of values and think about what this function were to look like, 0, 1, 2, 3, if x is equal to 0, anything to the 0 power is equal to 1, then we would have 1/2 to the first power, or in other words, 1/2. 1/2 to the second power, in other words, 1/4, 1/2 to the third power, in other words, 1/8. And if you were to think about what this function were to look like, again, it would go through this point 0, 1, but the values are getting smaller and smaller and smaller. So in general, when you have an exponential function, and again, the form for the exponential function is f of x is equal to a b to the x. A is any non-zero real number, and it's often called the initial value, or in other words, our starting amount, and we'll see why it's given that name in a bit. B is any positive real number not equal to 0. The domain, well, when you think about the domain of the exponential function, the domain will be all real numbers. The range will be all positive real numbers. Because if you raise a positive number or a real number to a power, your answer will be positive, all right? And the range, the y-intercept would be the point 0, 1, since anything to the 0 power we know is equal to 1. And the horizontal asymptote is going to be the, well, let's take a look at the horizontal asymptote. If we look at these graphs here, we can see that as x gets larger and larger with exponential decay, the horizontal asymptote would be the x-axis, and with growth, if we were to graph the number function the opposite direction, we can see that we also are approaching the x-axis. And so whether we have growth or decay, the x-axis is a horizontal asymptote of the function. All right, so let's take a look. Oh, so one note for the range. The range is going to be all positive numbers given that the initial value is positive. We know that this value here is going to be positive, so the sign of the overall function depends on a. So the range will be all positive real numbers if your initial value is positive, and it's going to be all negative real numbers if your initial value is negative. Okay, so let's take a look. Which of these are exponential functions? So the key to recognizing an exponential function is where the variable is. Where is your input variable? And the key to recognizing one is your input variable, x, is in the exponent. That's why they're named exponential functions. So let's take a look. Here, where do we find our variable? In the exponent. So yes, this is exponential. Here, where do we find our input variable, our x? Is it in the exponent? No. So this is not an exponential function. So exponential functions aren't just functions where we see an exponent. The x variable, the input variable, has to be in the exponent. Here, x is in the exponent. This is exponential. Here, x is in the exponent. This is also exponential. Here, why don't you try these? Which of these functions are exponential functions?